Oops.
College with tachycardia and
We'll talk about it later. I got you. All right, so look, linear equations and inequalities in one variable, right? Here's some vocabulary. Y'all can Google these if y'all like. All right. Algebraic statement, equation, inequality, strict inequality, conditional statement, solution, ordered pair, solve, linear equation, coefficient, equivalent equations, addition principle, multiplication principle, like terms, coefficient, identity, contradiction, literal equation. All right. And I know I owe y'all a video from yesterday. I got y'all. Y'all will get everything tonight, promise. All right. But again, this video, not on your test. Just let y'all know. You got to get that sticker, you know? All right, so look, algebraic statements and solutions, right? In the last chapter, right? I got you. So in the last chapter, right, we considered algebraic expressions, expressions formed by combining numbers and variables with the operations of addition, subtraction, multiplication, division, exponents, and roots. However, the only thing that we did with them was to evaluate them for given values of the variables involved. As soon as we took one step into the world of algebra, we quickly went right back into the world of arithmetic, evaluating expressions by performing operations with numbers. In this chapter, we will begin to see some important differences between the world of algebra and that of arithmetic. So, a mathematical statement is a comparison of two expressions by means of the relations of equality, right? Denoted by the symbol equal sign, as you can see, greater than with the, let me show you that in a second. I got cut off. Bear with me. This is going to be really cool. I feel you. My favorite resort is Rio. They got them all over the world. Rio. Yeah. All over the world. No, that's the resort. And then they have different places you can go. Yeah. It is. Sorry, I gotta look that up. I gotta look that up. Gotta look that up.
Service,
Mhm.
your own personal pool.
That's pretty good. That's pretty good. All right. Denoted by the symbol greater than, right? Less than is denoted by the symbol less than. And the compound relations greater than or equal to denoted by the symbol greater than or equal to, and less than or equal to denoted by the symbol less than or equal to. They can be broadly categorized as equations, those involving equalities, and inequalities are all the rest. All right. So the basic inequalities, less than and greater than, are called strict inequalities, while the compound inequalities are less than or equal to and greater than or equal to are sometimes called non-strict inequalities, right? The first thing to note about mathematical statements, unlike mathematical expressions, is that a statement may be true or false. For example, 1 plus 2 is equal to 3. That's an example of a true equation, while 1 plus 1 equals 5 is an example of a false equation. Both examples are equations, but one is true and one is false. In arithmetic, whether a statement is true or false can be completely decided by performing all operations, then comparing the resulting numbers. All right. So in algebra, however, this is not usually true. An algebraic statement is a mathematical statement involving algebraic expressions. A typical algebraic equation or inequality may be true or false depending on the values of the variable involved. Such a statement is called a conditional statement, right? By contrast, there's no conditional statements in arithmetic. Every statement is simply true or false, right? So since there are no unknown inequalities, I got cut off again. 1 second. All right.
God is telling us to take a break.
You want to take a break?
I'm just kidding.
We almost done. This is really fun.
It's simple. I don't know simple that won't be. You gotta give us an example, right?
Oh, yeah. Right now. So, for example, right? Consider the algebraic equation x plus 1 is equal to 4. The equation x plus 1 equals 4 is true when the value of x is 3. The equation x plus 1 equals 4 is false when the value of x is negative 2, right? These two statements show that the equation x plus 1 equals 4 is a conditional statement, since whether it is true or false depends on the value of the variable x. The fact that the typical algebraic statement is conditional prompts the following definition. We will come back to this definition over and over again throughout the text. All right. So, a solution of an algebraic statement, right, is a solution of an algebraic equation or inequality, and it is a value for each of the variables which, when substituted into the statement, make the statement true. Okay. Using this language, we can reformulate the results of the example, right? 3 is a solution of the equation x plus 1 equals 4, but negative 2 is not a solution of x plus 1 equals 4. All right. So basically, equations can be true, equations can be false, right? How many people in here want to be a lawyer when they grow up? Dang, nobody? Oh, okay. It's like that. All right. I know I kind of like law a little bit. You like watching it, but you don't want to be up there arguing it. Okay, okay, that's fair.
Sense. Yeah, I respect the law.
But you got to know the law to disrespect it.
Yeah.
Yeah, yeah,
It's not that I wanna break the law, I'm not a
Mhm.
criminal,
yeah.
but I just have no respect for the way the laws are carried out. So much inequality.
Got you. Okay, I got you. I got you.
You know what I mean?
Mm-hmm. But when you know the law, you could bend the law. You know,
I-
this is the beginnings of law. This true and false statement stuff. This is like big time in law, right? Mhm. It builds over time. So let's look at another example. Determine whether negative 2 is a solution of this equation. X squared plus 5x plus 6 is equal to 0, right? To determine this, all we have to do is just plug in the negative 2 and see what happens. Let's go. So, mhm, 2 plus 6 equals 0, right?
That become a +4.
Exactly, right? So negative 2 squared is 4. 5 times negative 2, that's negative 10. And we just add them together, right? And eventually we get down to 0 equals 0. This is what I wanted to get to, right? 0 equals 0. That means that this is a true statement, right? Negative 2 is an answer to this situation right here, right? This equation. Uh-huh.
-10, you subtracted 10 from four from the.
Add the 4 and 6 to get positive. Oh, wait, no. 4 plus negative 10 is negative 6, and a negative 6 plus 6 is a 0. Yeah. And 0 equals 0. So it's true, right? So x equals negative 2 is a solution of this equation, right?
That's what it was asking, right? If
Yeah.
that-
Right. If that could answer the equation, right? All right, let's look at another example real quick. All right. A little bit different.
Actually interesting, I'm shocking myself. It's actually pretty interesting.
Awesome. You can do the homework for it after the test.
Sure.
After the test. This is not on your test, right? Okay. So let's determine, right, if negative 3 is a solution to this equation, x squared plus 5x plus 6. Yes, it's the same equation as before, right?
Square be -9 or +9?
Positive 9.
So +9 plus -15, so that
Mhm.
would be 15 take away. This would be negative.
Mm-hmm. So 9,
-6.
9 minus 15, negative 6.
+6 is 0, so it's still true.
Perfect, right? So we substitute negative 3 in. We have negative 3 squared plus 5 times negative 3 plus 6, which eventually gives us 9 plus negative 15 plus 6, which equals 0. eventually gives us -6 plus 6, and then we have 0 is equal to 0. So this equation is true when x is equal to -3. So -3 is a solution of the equation x squared plus 5x plus 6 is equal to 0. Right? Right? That's good. Half your test is like this. Yeah.
Question, because it's
Mhm.
different work.
Yeah.
So for example, when it's, so you see,
Yeah. Hmm.
so Professor, you see how the five X, right?
Hmm.
So because it was a -9 plus the five, it's always basically gonna be subtraction, not addition, correct?
+9 times a -15 plus a -15, excuse me. Yeah. So different signs, you subtract and keep the sign of the larger number.
Okay, right,
Yeah.
right, there you go.
Yeah.
I, I get my ass kicked with those confused.
But you don't have to memorize it though, because you have a calculator. You can verify it.
Yeah.
Mhm.
I'm trying to so far.
I got you. Yeah.
Negative number. Really? It always says error.
It does it.
Is there a different way I have to like study?
I'll show you. I'll show you. Before I leave, ask me again and I'll show you. Yeah. I'll do it on the fancy one on the computer. All right. So notice that in the previous two examples, we found two different solutions to the same equation. In the case of statements with more than one variable, we need to specify a value for each variable in order to specify a solution. Many times we will encounter equations or inequalities in two variables, x and y convention, right? So when specifying a solution of an equation or an inequality in two variables, x and y, we will use ordered pair notation. So an ordered pair is a pair of two numbers grouped with parentheses. For example, a typical ordered pair might be 4 comma 7. In this case, the first number will always represent a value for the x, while the second number will always represent a value for y. A full treatment of two variable statements is found in the next place or next chapter, right? However, we can already get a feeling for them in the context of deciding whether a given ordered pair is a solution or not. All right. So let's look at this example. We want to determine whether 1 comma -2 is a solution to the equation, right? This is a fancy way of me telling you plug it in and see if it works. Let's try it out.
Also, X is one and Y is -2.
That's it. So this is going to be what? 3
Three
times 1 plus
plus
4 times -2. And I want to know, does that equal 11?
so four
That's it.
plus two
So this would be,
plus
so this would be 3 plus -8, right? And I want to know, does that equal 11?
no, because aren't we supposed to do a takeover three,
Right? Which is what?
which isn't that -5?
So -5 does not equal 11. So it's not a solution to the equation. That's simple. Right?
See, there's a friend out here.
Ugh,
Thank you,
that's not bad.
thank you.
It's that simple. That's all it is. All right. Let's try it again.
Being wrong.
Not necessarily. Let's try another one. A little bit different. Oh no, the next one's way easier than this. Pharmacology is mad easy. Yeah. Oh, conversions. Conversions, yeah. So like how many cups is in a milliliter? Or how many milliliters are in a cup, whatever. That's the right question. Yeah. Yeah. It's mad easy though. Yeah. Yeah. So look, we want to determine whether 5 comma -1 is a solution of the equation 3x plus 4y equals 11. So 3x plus 4y is equal to 11. It's true. Let's see. I don't know. I didn't do it yet. So this would be times 5 plus 4 times -1. And I want to know, does that equal 11? I don't know. 15 minus 4, does that equal 11? All right, so 11 equals 11, so that's an answer. That's true. Okay. So they're gonna be like, yo, true or false? That's it. Good. Yeah. Good, good. I'm proud of you. Yeah. Let's try another one. Mm-hmm. It's gonna build into something in statistics. Yeah. We not there yet, but yeah, we getting there.
You know what's crazy?
Yeah.
The one part of math.
Yeah. Really? This the hard part of the class.
Part.
And this the hard part of class.
Sorry?
Yeah.
No way, what you did in the first 3 years was terrible.
They're not gonna let me teach it. Yeah. 'Cause nah, they mean over there. They mean. Yeah. They barely let me tutor it. Mhm. But I do know pharmacology. Yeah, the teachers are mean. The nursing. Yeah. They're mean to me. They're not mean to y'all. They're just mean to me. Yeah. Yeah. I'm pigmentally challenged. Pigmentally challenged. So determine whether negative half is a solution of this inequality. Let's check this out. So look, all I'm telling you to do, just plug it in. No stress, just plug it in.
Um, does that,
And I want to know
what does that equation mean right there after the one?
which one. Greater than or equal to, right? So I want to know, is that greater than or equal to -1? Let's see, right? So this is going to be 5 times negative half. This becomes what? -5/2 plus 1/1. And I want to know, is that greater than or equal to -1? Let's see. You know, in order for me to add fractions, it is, right? Let's see. In order for me to add fractions, I got to have the same what? Denominator. And so what's my LCD? 2. Multiply this by 2. But what I do to the bottom? All right. So now I have what? -5 plus 2 over 2. Is that greater than or equal to -1? I don't know. What's -5 plus 2? Mm-hmm. No, no. Like you owe me $5 and you give me 2. How much you owe me? 3. All right. So -3/2. And what I want to know, is that greater than or equal to -1? Is greater than?
Isn't one greater because it's one whole?
Hmm?
Isn't
Yeah.
one greater?
Is it?
No, why is it one greater?
Is it?
I thought one was greater because it's a whole.
All right, let's change it. Let's change this into a decimal, right? What's 3 divided by 2? Hmm.
5? Yeah. Okay.
I'm impressed.
So.
So,
It would be.
so is this true? Is that true or is it false?
It's false. Yeah.
Why?
It's a, yeah, it's a negative, a negative is less than a positive, no?
Uh-huh.
So that's why. So it would be greater.
Mm.
Wait, it's equal.
It is false, I'm trying to see if you guys understand why it's false. Mhm.
Okay, first of all.
They're both negative.
Oh, wait.
But one of the negatives is bigger than the other negative. Yeah.
1.5 is like. Because so which means it's like further down the line.
So which one of these two numbers is bigger? Which one is bigger? The -1 is bigger. Right. So this is a false statement. Yeah. Exactly. Exactly.
She said the negative one was closer to being a positive, it was closer to the positive
It's
side.
closer to 0. Yeah.
That's what she
Than
did,
the
right?
-1.5, right? Yeah.
Right.
Mhm. Very good.
Very good.
So that's it. Hold on. Technically, I should do this. I should do that. I should have put a line through it. My fault.
Oh, this is great, Professor. I kind of sort of follow.
That's good.
Oh, don't worry. It's not- I mean, it's not-
Hey. All right, almost done. All right. So, right? So we close this section with one of the most important definitions in this text, solving an algebraic statement. To solve an algebraic equation or inequality means to find all the solutions. So every word in the definition is important, right? Not yet. We got time.
I understand.
All right, so here's some definitions for it. So solutions, right? So to solve an equation or inequality, we need to keep in mind what a typical solution looks like, right? Is it a number, as is in the case of statements with one variable? Is it an ordered pair, as in the case of statements with two variables? All, right? So to solve an equation or inequality, we need to know how many solutions the statement has. Does it have one solution, two, infinite many, or none? Right? Those are all possibilities that we have. Find. Rather than guess solutions and then check whether in fact they are solutions or not, we would like to have a procedure that produces or finds a solution for us. All right. So let's look at solving linear equations in one variable. In this section, our goal will be to develop a method that will find all the solutions for certain equations in one variable. Let's start off with a very, very, very simple example, right? So solve for x equals -2, right? So one solution of the equation is obvious, -2. Just to make sure, substituting -2 equals -2 is a true statement. On the other hand, it is just as obvious that any value of x which is not -2 will not be a solution of the equation, right? -2 equals -2 is a true statement. Yeah, yeah. So that's like a really, really easy example. Yeah. All right. Mm-hmm. No, it could be anything. Anything, yeah.
Everything not be this simple.
I promise you it is. You have formula sheets. You don't have to memorize nothing. All right. If only it were so easy to find the solutions to every equation. In fact, our first goal of producing a method to find all solutions to a given equation will be to convert it to an equivalent equation that has the same easy form as our very, very easy example. We say that two equations are equivalent if they have exactly the same solutions. In order to do this, let's first specify what made our very, very easy example so easy. One side of the equation is a number. All operations involving numbers have been performed. The other side of the equation is an algebraic expression containing just one variable and no operation. One sometimes says x is by itself on one side of the equation, right? So a consequence of the second item is that the equation is linear. So a linear equation is an equation where the only operation performed on the variable are addition, subtraction, and multiplication by a constant called a coefficient. So for example, the equation 3x plus 4y equals 11 is a linear equation with two variables. The equation x squared plus 5x plus 6 equals 0 is not a linear equation because the x squared term involves a variable raised to a power different from 1. So the remainder of the section will be devoted to the following sentence. Show you.
One, that makes it linear.
That makes it linear,
And
right?
because it was raised above one, that makes it non-linear.
Right. Exactly, right? So every linear equation, almost in one variable, let's say x, is equivalent to an easy equation of the form x equals something, right? So the blank will be a number. This is what your solutions will look like, right? So there's an important consequence of this fact. Almost every linear equation in one variable has exactly one solution, right? Very easy. Right back.
That whatever this is leading to is diabolical.
No, no, no. It's simple. So basically, what I'm leading up to is I'm going to give you linear equations, and I want you to be able to solve them, right? Yeah, yeah, go ahead.
Because if not, I'm gonna
But
forget.
but let me be clear, it's not on your test. All right?
Yes.
Yeah, yeah, yeah. Unless you're curious, then the homework is already posted. Huh? Each test is a midterm.
Oh,
So think of it like that. You're gonna have two tests by midterm. Yeah, yeah. All right, so let's talk about the rules of the game, right? So given any linear equation in one variable x, no matter how complicated, we will develop a method to find an equivalent equation of the form x is equal to blank. Then we will be able to read off the solution to the easy equation. It will also be the solution of the maybe more complicated original equation also. The method will be based on the following two properties of equations. So the addition principle, adding or subtracting the same quantity to both sides of the equation will produce an equivalent equation. The multiplication principle, multiplying or dividing the same non-zero quantity to both sides of the equation will produce an equivalent equation. These properties can be summarized in the loose slogan, doing the same thing to both sides of the equation does not change the solutions of the equation. As usual, with loose slogans, though, we should be aware of the fine print. For example, multiplying both sides of an equation, which may be false, by zero, will yield an equation zero equals zero, which is always true, right? So applying the rules, solving linear equations. So we will use the properties in the previous section to attempt to start with any linear equation in one variable, say x, and obtain an equivalent equation of the form x equals blank, all right?
I'm a
So
little
we
lost,
building it
so
back.
we're gonna work on this more, come
Yeah.
back.
Yeah, yeah, yeah. Let me do one example real quick, and you'll see like what it is I'm talking about. Like I'm literally talking about just solve for x.
Oh,
That's all I'm saying. Yeah, that's it. Just solve for x.
yeah.
Kind
What
of.
we,
Kind of. It's more simple. So look, since the equations have the same solution, this solution will be obvious by considering the simple equation. Recall that one of the special features of the easy equation x equals blank is that the expression with the variable has no operation involved. Our guiding strategy for solving linear equations will be to identify the operations involved in the expression involving the variable and then to undo them one by one by using the addition and multiplication principles, right? So for example, I would say I want to solve x minus 41 equals 36. How would I do that? Somebody tell me.
41.
Hey, that's it. That's it. That's it. You put all the x's on one side, you put all your numbers on the other, right? So x equals what's that? 77? Boom. Yeah.
You're on 41.
Yeah. I added it.
36.
Yeah.
Then what you do to the left side.
Because the thing is, I wanted to get rid of the negative 41, so I have to add it. Right?
Okay.
Yeah. So like literally like that's this entire section, solve for X. You know? Y'all want to see another example? Y'all feel like y'all get it. I got you. Here's a harder example.
Negative, like that.
All right.
Okay, that's right, Ken.
It's gonna take 2 seconds, this example right here, right? So let's say I want to solve, right? 5x plus 18 equals 12, right? Tell me what I would do. So what am I doing to the 18? How do I get rid of a positive 18? Subtract what? Right? I'm gonna subtract 18 to get rid of it on this side. What you do to one side, you do to the other. So, no, no, you do the same thing to the same side, right?
Yeah.
Subtract 18 from both sides, so you have -6. What do I do after that? Not -5, not -5. Divide by 5, right? Because this is 5 times x, right? So I want to do the opposite, division. But what you do to one side of the equation, other side of the equation. Here's your answer. X equals -6/5. Yeah. Yeah. I'm sorry? Yeah, yeah, yeah. Yeah, yeah. So you always do the opposite operation to get rid of it. Yeah, that's a trick. Yeah. It was?
I'll do one more,
Yeah, sure.
like that, like do it like complicated like that.
Yeah, yeah, yeah. I got you. I don't care about decimals.
Yeah, there was a decimal one. It was 0.2.
Y'all can put in fractions into the homework. Yeah.
Right. The other one was I.
It's like you have $12, but you buying something for $18. How much you owe them? Yeah. See?
About that chart.
Exactly. Exactly. Yeah. That's what I'm always thinking about. Yeah. Exactly. But y'all, one more example after this. But basically, like y'all have the calculator, so y'all can verify this. You know? All right, real quick. Sometimes we will encounter statements with variables on both sides of the equation or inequality. In this case, we will need to take an extra step to make sure that the equivalent equation has variables on only one side of the statement. Like our easy equation, this can be done using the same solution, excuse me, the same addition principle that we have been using so far. But we need to make one thing, right? Sorry, but we need to make one thing that we have been using behind the scenes more explicit. In a linear equation in one variable, like terms are identified according to whether they involve the variable or not. In other words, terms involving the variable will be like terms, and terms not involving the variable will be also like terms. The most important feature of like terms for now is that like terms can be added or combined, right? So when we add like terms involving variables, we add the coefficients of the terms, but leave the variable part the same. For example, in the expression 5x plus 2 plus 3x plus 9, right? The terms 5x and 3x are like terms. So you will add them to get 8x. Likewise, the 2 and the 9 are like terms. So you will add them to get 11. So 5x plus 2x plus 3x plus 9 is equal to 8x plus 11, right? When we use the addition principle, we will make a habit of writing like terms in the same column, right? For example, say we want to solve this, right? Same example. Solve for x, right? I have 3x minus 9 is equal to 8x plus 7. I just want to solve for x. Real simple. Tell me what to do. Well, how do I get rid of 3x? That's what I'm trying to do. Combine the x's and combine the numbers. Divide what? No, no, no. First, I got to get all my numbers on one side, all my x's on the other. Plus 9. Okay, I'm going to plus 9 over here. But what I do to one side, I have to do to the other, right? So now I have what? 3x is equal to 8x plus 16, right? What's next? No, not the 3x, the 8x, right? How do I get rid of it? All right, so I'm going to subtract 8x from over here. But what I do to one side, I have to do to the other, right? So what is 3x minus 8x? So negative 5x, right? Equals 16. And what should I do after that? Divide by -5. Perfect, right? What you do to one side, you do to the other. So final answer, x equals 16 over -5 all of the day. Go ahead. So looking back at the original question right here, right? So whatever sign is in front of it, I'm doing the opposite of it. Yeah, that's it. So let's see. Got you. Go ahead. Go ahead. I do have a more complicated example if y'all want to see. All right. All right. Last example then. Last example. We'll tap out right here. All right. But y'all gonna like this example though. This involves multiplication, addition, all of that.
All the bottom. So you get the last one.
All right, last example. So looking at the two methods above, the second method has the advantage that the coefficient of the variable term is positive after using the addition principle to obtain an equation with the variable on one side only. That is because in the original equation, the variable term with the larger coefficient was on the right. From now on, we will follow the custom of writing our equivalent equation with the variable on the side where the original coefficient of the variable term was larger. The only thing that can make a linear equation in one variable more complicated than the examples we have seen before is that if there's more operations on one or both sides of the equation. For example, we may have to perform multiplication using the distributive law if necessary, or we may have to combine like terms on one or both sides separately. The following example illustrates the situation. Notice that before we begin to apply the addition or subtraction principle, doing the same thing on both sides, we will perform operations on each side separately. So this is more complicated. Check this out. But it's not bad though. Right?
Well, how do you isolate the exodus in the parentheses?
Before I do that, what should I do first? Huh? Right. So what do I do? Tell me what to do. Yeah. Exactly, right? You're gonna distribute the four.
That's 4 times -3.
So what's 4 times -3?
-12.
Perfect. Plus 2x equals 7x minus 9. What's next? No.
No, wait. 4x plus 2x.
Exactly. I want to combine like terms. So 4x plus 2x, this becomes 6x minus 12 is equal to 7x minus 9. What's next? Let's work on the x's. Tell me what to do. You want to add 12 over here? Okay. I got you. 7x. What's that? Plus what? 3? 15 or 3? Like you have $12 and you bought something for $9. How much you have left? 3, right? All right, what's next?
Plus 3.
No.
Still gotta combine the -7.
Right, I'm gonna subtract 7x over here. What I do to one side, I have to do to the other. So now what do I get? Negative x, very good, is equal to 3. How do I get rid of the negative that's there?
Plus 3.
No.
No. Well, why divided by x?
Divided by what? No, by -1, right? That's how I get rid of it. And what I do to one side, I do to the other. So final answer, x equals -3. And that's it. Uh-huh. Yeah.
-1.
Yeah. Yeah. The smarter thing to do in this question, right, is you see right here, right? When we have the 6x minus 12 equals 7x minus 9, subtract the 6x from both sides and then add the 9 on the other side, and you would have just got straight to the final answer.
Or you
Right?
like use the one.
Yeah. Okay.
If you have an x, there's always an invisible one.
Yeah.
That's why you divided it by the.
So this is what I'm saying. Go ahead. I'll catch up with you. So 6x minus 12 equals 7x minus 9, right? Thanks. So look, this is what I was saying. If you deal with the x's first, right? Say we subtract 6x from here, right? So now we have -12 is equal to just x minus 9. Then you add 9 and you're done with the question. So -3 is equal to x. Right. So like that's one way to do it. Your way is fine too, as long as you remember to divide by the -1. Right. Yeah. Hey, you got another question?
Yes.
Let's go over it. Let's go over it.
I got.
Awesome. So walk me through these. How you got these? These are so you squared these, right? Okay, that's good. Perfect, perfect. And you added these up, right? Just the individual 4.2.
That's a good.
Wait, no, you did it up here, right? 22, right? So that's 22 right here. And then the eight, no, wait, I'm lying. The 22 is this, where it says 3.67. That's 22. And then that's it. Little math and you got it. Yeah. And then remember, that's the variance. So to find the standard deviation, you got to square root the final answer of that. All right. Hey.
Okay.
All right. How's everything good? Awesome. I'm gonna stop sharing. I owe you guys